Okay, so good morning. I'm Álvaro Gómez-Morón, PhD student at Hospital Universitario de la Princesa, and I'm going to present the data we published this year, which titles End-binding protein 1 regulates the metabolic fate of CD4 T lymphocytes through the organization of the mitochondrial network. For full T-cell activation, the classical three signals are required. The first one is the antigen presentation, the interaction between the TCR and the peptide loaded into the MHC of the antigen-presenting cell. The second one is the co-stimulation, and the third one is the integrin binding. These three signals converge in the assembly of the LAT complex, and this complex is at the diversification point for the signal that promotes the actin cytoskeleton reorganization, the polarization of the centrosome, and the translocation of different transcription factors to the nucleus of T cell to achieve the T cell activation. This interaction between the T cell and the antigen-presenting cell conforms a structure called the immune synapse, which is a cell structure that allows platform signaling for T cell activation and effector function. So this immune synapse is organized in concentric SMACs or clusters of supramolecular activation, and as we can find in the central SMAC, there are the TCR and CD3 microclusters. In the peripheral SMAC, we can see the contractile actomyosin arcs and the addition molecules such as LFA1. And in the distal SMAC, we can find the filamentous actin. So this immune synapse is a highly dynamic structure, and this is because of the cytoskeleton, as we can see in the following videos. In the left one, we can see the retrograde flow of F-actin that allows the mobilization of those molecules and TCR CD3 microclusters. And in the right one, we can see the translocation of the centrosome, or mTOC, which is important for the mobilization of different organelles and vesicles at the immune synapse. So the protein which focuses this work is end-binding protein 1, or EB1. This protein belongs to the plastids family of proteins that accumulates in the microtubule plus ends and are regulating the microtubule dynamics and growth, preventing the microtubule catastrophes, as we can see in this video. EB1 regulates different functions in the cell, such as the chromosome segregation and cell migration. And in this work, in 2012, it was discovered that EB1 regulates the organization of the immunological synapse, and this is because of its interaction with CD3 or TCR zeta. So, with this in mind, and due to the importance of the tubulin cytoskeleton to the localization of the mitochondria at the contact site of the immune synapse, we decided to study the role of EB1 in the control of the mitochondrial network and T cell metabolism during T cell activation. So, first we decided to study the proximity between EB1 and the mitochondria, and for this we used CD4 T lymphoblasts, we fixed them, and we stained for EB1 and mitochondria. We analyzed them by confocal microscopy, and here we can see a 3D reconstruction using IMARI software. And as we can see in this image, in yellow EB1 tips that are close to mitochondria, and in blue EB1 tips that are far to mitochondria. And as we can see, we observe that always we can see mitochondria, we see EB1 tips close to them. So, to study what role was developing EB1 with these mitochondrial T cells, we decided to silence EB1 expression in CD4 T lymphoblasts and study by confocal microscopy the architecture of this immune synapse. As we can see in control cells, we can see a proper polarization of the mitochondria of EB1, which is enriched in the centrosome area, and of CD3 zeta. Here we can see a 3D reconstruction of the SMACs, and we can see that mitochondria are in the peripheral SMAC, and the centrosome and CD3 zeta are in central SMAC, but when we silence the expression of EB1 in CD4 T lymphoblasts, we can see a decrease, an alteration in this structure of the immune synapse. So, as I have said, the importance of the tubulin cytoskeleton and the actin cytoskeleton in this localization of the mitochondria, we decided to study also by confocal microscopy the tubulin and actin cytoskeleton. And as we can see in these images and in the quantification below, we see a decrease in the polarization of the mitochondria to the immune synapse, an increase in the centrosome or mTOC distance to the immune synapse in EB1 silent cells, and alteration in the polarization of F-actin. So then we decided to study one of the principal functions that perform mitochondria, which is the mitochondrial respiration, and for this we use the Seahorse extracellular flux assay by measuring the OCR, which is an indirect measure of cellular respiration in control and EB1 silence CD4 T lymphoblasts in resting condition and after stimulation with anti-CD3 and anti-CD28 antibodies. And as we can see in this graph and in the parameters calculated from this graph, which is, that are maximal respiration and ATP production, we can see a decrease in the maximal and ATP production in EB1 silence CD4 T cells when stimulated, and also these cells did not respond to the stimulation. So to study if this difference were because of EB1 silence CD4 T cells have lower amount of mitochondria, we decided to stain these cells with NOW, which is a proof that inform us of mitochondrial mass, and we see no difference in the number of mitochondria in these cells. So it's known that EB1 silencing in other cell types promotes mitochondrial dependent apoptosis, so we decided to study apoptosis through the fast ligand system in control and EB1 silent cells in non-stimulation, stimulation with anti-CD3 and anti-CD28 antibodies, and stimulation plus CH11, which is an apoptotic inducer, and CH11 and DX2, which is a fast antagonist that blocks the function of this CH11. So in basal conditions, we can see a 93% of light cells, but when we stimulate these cells, we can see an increase in the early and late apoptosis cells in the EB1 silence CD4 T cells. So, and when we add the CH11, we can see also an increase in the cells in early and necrosis. So in this graph, we can see a summary of what I have explained. In resting conditions, we can see difference, but when we activate these cells, we can see an increase in the apoptotic early and late apoptosis in silenced EB1 cells. When we use the DX2, we can prevent this apoptosis, but when we just use CH11, we can see an increase in this apoptosis, and this apoptosis is higher in EB1 silent cells. So, taking into account this alteration in cellular respiration and in the survival, we decided to study the mTOR signaling pathway that regulates, among other processes, the cytoskeleton organization, the survival, and the metabolism. So, for this, we used control and EB1 silent cells. We stimulate with anti-CD3 and anti-CD28 antibodies, and we determine by Western blot dephosphorylation and thus activation of different molecules of this pathway, such as AKT, mTOR, and S6. And as we can see in these plots and in the quantification, we can see a decrease in the phosphorylation in AKT, mTOR, and S6. So, as I have said, this pathway regulates several processes, but in T cells it promotes the glycolysis. So, we decided to study the glycolysis by using the seahorse extracellular flux assay, but in this case we measured the ECAR, which is an indirect measure of the glycolysis, and we did it in control and EB1 silent CD4 T lymphoblasts in resting condition and after stimulation with anti-CD3 and anti-CD28 antibodies. As we can see in the graph and in the parameters, EB1 silent cells has a decrease in the glycolysis and glycolytic capacity when activated, and also these cells did not respond to the stimulation. So finally, the conclusions of this work is that EB1 is regulating the organization of the immune synapse and the apoptosis, and this is because it connects the reorganization of tubulin cytoskeleton and mitochondria with the metabolism of T cells. Finally, I want to thank all the people that have participated in this work, to the committee for allowing me to present this data, and you for your attention. Thank you.
Thank you. Is there any question for this presentation? There's a question over there.
Hi, Álvaro. Nice talk. I don't know if you've done it yet or you plan to do it, but have you looked at long-term effects on the T cells that lack EB1 in the sense of how they polarize? Do they establish long-lived memory cells and all these kind of questions? Or is that something?
Repeat the question, please?
Yeah.
Can you repeat?
The effect of the knockout of EB1 in the long-term function of T cells in response, for instance, to polarizing signals, polarizing meaning Th1, Th2, Treg, and establishing of memory, long-lived memory in the T cells, because they are more sensitive to apoptosis, but I don't know whether that's kind of acute stimulation or it might happen upon repeated stimulation as well.
Yes. We didn't study this polarization because the immune synapse is a highly dynamic structure and is very rapid events. So we decided to perform experiments that can inform us about these short events. But it's a good idea to try this. Yeah. Thank you.
Any question? Have you, I don't know, I'm just thinking, do you think there could be different parts of the EB1 molecule that could be related to the different functions, like related to interaction with mTOR? So you can map different mutants and then dissect the functions, or?
Yes, EB1 has different mutants that allow the interaction with other plastids of the family, but I don't know if there is any domain that interacts with mTOR or AKT, but I have to read about it. Thank you.
Thank you. Thank you.